In this video, I'm going to attempt to derive the Clausius-Clapeyron equation, but before we go ahead and do that, I think it pertinent that we discuss what Gibbs free energy really means, and when we can find an equivalence in what it really is. So, to do that, we are going to talk about equilibrium, and what is really equal at equilibrium, which you may have guessed by my last sentence that it will be Gibbs free energy. And to do that, let's go ahead and draw some sort of container here. And in this container, let's say it's isolated from the outside environment and that I have some sort of phase equilibria here. And we've talked about this a lot in my videos in the past. However, it will be, again, very useful for us here. So we have some number of moles of this substance in its vapor phase. I'm going to denote that with a little v here for vapor. And we have some moles of this substance in its liquid phase. There we are. And we have this phase equilibria right here, this transition phase. And at that phase, we've talked about how we have equal concentrations and of both the vapor and the liquid components. However, what we will find to be interesting about these two phases is that at that phase equilibria, we are going to see an equivalence in the Gibbs free energy. Now, let's go ahead and derive that. So, we're going to talk about, in this derivation, the Gibbs free energy of the liquid phase and the Gibbs free energy of the vapor phase. So, I think it first pertinent that we discuss a couple ground rules, I'll call them, for this scenario here. The differential of Gibbs free energy times the moles will be equal to 0. Similarly, we will need to discuss that, obviously, this may seem obvious, however, we need to discuss that the moles of the liquid plus the moles of the vapor of this component will equal the total moles of the component. Now, sometimes this is put in parentheses, so I'll go ahead and put this in parentheses here. Now, with all of this out of the way, I think we can go ahead and discuss the total Gibbs free energy equations here. And to do this, we will say that the number of moles of the liquid phase times the Gibbs free energy of the liquid phase plus the number of moles of the vapor phase times the Gibbs free energy of the vapor phase will equal number of moles times the total Gibbs free energy. Taking the differential of this equation, we will have to do some sort of product rule to these two terms. So let's go ahead and do that right quick. And we have already said that this right-hand side of the equation here will go to 0 earlier. Now, from this, we can go ahead and pull out some components here. So, the change in Gibbs free energy of the liquid phase. Actually, what we would rather do is write one more equivalence for this equation here. And that equivalence is going to be that the moles of the liquid phase, well, rather the differential change in moles of the liquid phase, should be equal to negative differential change of the moles of the vapor phase. And the reason for this is that, obviously, when one mole goes from the liquid phase to the vapor phase, then you are losing 1 mole of the liquid and gaining 1 mole of the vapor, right? So that equation makes sense as well. And by defining that, we can then write another equation here, we can factor out the differential change of the moles of the vapor phase and multiply that by the Gibbs free energy of the vapor phase and then subtract the Gibbs free energy of the liquid phase. And then we can just add our other two terms on here. Now, from here, what we can do next is discern that at a constant temperature and pressure, as is present in many equilibrium states, the change in Gibbs free energy should be equal to 0. So therefore we can write this equation here. By canceling out this term at 0 and this term at 0, we are thereby canceling out these entire terms. Now, with this equation, it is fairly easy to see that by dividing by d and v, we are given this equation, or rather, that the Gibbs free energy of our vapor phase is equal to the Gibbs free energy of our liquid phase. And this is the equivalence that we are talking about when a substance is at equilibrium. So for any two pure components, note we didn't stipulate which components, or what substance rather, we have here, but for any two components, at any two phases truly, although liquid and vapor are the most common, we can denote that the Gibbs free energy will be equal to one another at the equivalence point. That is the equivalence that we can see in this container. Boom! Changed clothes. And apologies for my voice for the rest of this video. I did have a show last night in which there was a lot of projection required. So, in this part of the video I intend to derive the Clausius-Clapeyron equation, in which I will relate the saturation vapor pressure of a substance to the temperature of the system. So we are going to do this from the differential form of the first law as well as the definition for Gibbs free energy. So let's go ahead and write down the differential form of our first law here, which is going to be the differential of internal energy is equal to the differential of heat. We're going to talk about a reversible process times the differential of work, and again this is reversible. So from here what we intend to do is basically, because we call these reversible processes, we can write heat as temperature times the differential of enthalpy, and we can subtract from that pressure times the differential of volume as our reversible work term for a system of one pure component. Now, from here we can go ahead and use the definition of enthalpy, or rather the definition of differential of enthalpy, being dH is equal to du plus P, or rather the differential of pressure times volume, which, again, if we were to rewrite that, would be du plus P dV plus V dP. Substituting in our differential of internal energy term from up here, we will then have Td, temperature differential of enthalpy, minus pressure differential of volume, plus pressure differential of volume, plus volume differential of pressure, and we will see a cancellation right there. Alright, now from there, let's go ahead and use our definition of Gibbs free energy, which is going to be H minus T ds. Yes. Now, From here, what we're going to do is go ahead and take the differential of Gibbs free energy, or rather TS, my bad. That should be H minus TS. I'm skipping a step and going right on to the differential. Let's go ahead and differentiate this then. We went dH minus d of TS, which again will be equal to, we're just doing product rule here, so minus dt, or SDT, minus TdS. Now, again, substituting in our term for the differential of enthalpy that we've already derived, we will get TdS plus VdP minus SDT minus TdS. And again, we will have a cancellation there. There we are. So our differential of Gibbs free energy will be volume times the differential of pressure minus entropy times the differential of temperature. Now all of this has basically been done mathematically by the terms that we have basically described solely in terms of one another, right? Enthalpy was derived from the definition of internal energy. Same with Gibbs free energy. That's kind of a humanly constructed term there. So what we want to do then is we want to kind of think about the actual system itself. And let's say in our system that's potentially has some sort of movable boundary in it. I will erase that top there and give it some sort of movable piston boundary. And let's say we have, again, we have some liquid and we have some vapor, right, in this system of our pure component. Now, what we have here, we have to have some sort of relation in order to have this equilibrium or phase transitional boundary here, right? There has to be some equivalence in nature. Now that equivalence, as we're about to see, is Gibbs free energy itself. The reason being that the differential of Gibbs free energy has to be equal to 0, which therefore means that the Gibbs free energy of the liquid phase is equal to the Gibbs free energy of the vapor phase. The reason again for this is that in this isolated system here with this phase boundary there, we have no change in pressure of the system and we have no change in temperature of the system. So both of these, this change in pressure would go straight to 0 and this would go straight to 0, and again we were equating that to the differential of Gibbs free energy. So therefore, our differential of Gibbs free energy for the system is indeed itself 0. So we now know that the Gibbs free energy of the liquid phase is equal to the Gibbs free energy of the vapor phase. And from there, we can, again, basically rewrite our equation for the differential of Gibbs free energies as being equal to one another. So we can say the volume of the vapor phase, and I'm going to try not to confuse our V's here by explaining each one, times the differential of the pressure. Now this should be our saturation vapor pressure, as this is the pressure that we would be measuring in this scenario, minus the enthalpy of the vapor phase times the differential in temperature is going to be equal to the volume of the liquid phase times, again, our saturation vapor pressure minus the entropy of the liquid phase times the differential in temperature. And from here, what we are going to attempt to do is basically move all of the vapor, or let me rephrase. What we want to do here is we want to move all of our pressure and volume terms to one side of the equation and all of our entropy and temperature terms to the other side of the equation. And when we do that, we're going to see that, let's see, I'll move liquid to this side and then to that side. So we'll have volume of the vapor phase minus volume of the liquid phase, all times the differential in temperature, is going to be equal to the entropy of the vapor phase minus the entropy of the liquid phase times the differential in pressure. And again, that's the saturation vapor pressure. That's what we're trying to derive the equation for in general, remember. So, now that we have this, we could basically state this again as the change in entropy or the change in volume times these differentials in pressure and temperature. However, I'm not going to write that here. So, we can go back then to our first definition of Gibbs free energy, and from there, I believe we went ahead and we derived an equation that will come up with a substitution here. And that substitution should be... Okay, so we have, let's see, we have Gibbs free energy being equal to enthalpy minus the temperature times entropy. And we said that the Gibbs free energy of the liquid phase would be equal to the Gibbs free energy of the vapor phase, right? So therefore, we can basically take the expression here and write it in terms of the liquid or in terms of the vapor phase and set that equal to each other. So we can say the enthalpy of the liquid phase minus the temperature times the entropy of the liquid phase is going to be equal to enthalpy of vapor minus temperature times the entropy of the vapor phase. Again, moving these terms to their respective sides to basically be with one another, we would get the enthalpy of the vapor phase minus the enthalpy of the liquid phase is equal to the, let's see, and oh boy, the entropy of the vapor phase minus the entropy of the liquid phase times a negative temperature. Let me make sure I did that algebra correctly, because I did switch sides of the equation as well. Yes. I think I did that correctly. Except the temperature, if I'm putting a negative here, then the temperature sign should become positive. So then, swapping the temperature, dividing by temperature on both sides of the equation, I will obtain this expression, and the enthalpy of the vapor phase minus the enthalpy of the liquid phase is more commonly referred to as the change in enthalpy of vaporization over temperature. There we are. So then we can substitute that back into our original expression there. We can substitute this in for this and obtain this expression. Okay. Now from here, what we can go ahead and do is we want to again move the terms to their proper sides. So this time what I think I'm going to do is put the differentials together. And what that's going to do is end up with an expression that looks like this. Change in enthalpy of vaporization over temperature times volume of the vapor phase minus the volume of the liquid phase is equal to divided. Okay. Differential of pressure saturation over the differential of temperature. And now, what we have derived here, this is generally referred to as the Clapeyron expression. Oh, excuse me. Clapeyron expression. Right? Okay. So we've now derived this expression, and our goal here then is to kind of remove the differentials from this equation in order to get a more consistent definition for the changes in temperature. And to do that, we're basically going to solve this as a differential equation. To solve this differential equation, we must first go back and look at our diagram here. And from our diagram, we can make an assumption about the system. We can say that the volume of the vapor phase is going to be much greater than the volume of the liquid phase. Now, the other assumption that we are going to go ahead and make is we're going to define the volume of the vapor phase as following the ideal gas law. So we can say the volume is going to be equal to gas constant times temperature over pressure. Now we're basically going to ignore the liquid phase component at this point and rewrite the Clapeyron expression as such. Alright. So from here then, we are going to simplify this expression a little bit. And let's try and simplify this. So first I'm going to multiply temperature into the denominator here. Now I'm going to go ahead and multiply both sides by dt and divide both sides by psat. Alright. Now from here, we have separated our variables. And at this point, we can virtually solve this equation by methods of integrating both sides. So, assuming that the change in enthalpy of vaporization is constant for our system, we can treat it as a constant and the ideal gas constant as constant, and the expression we will then arrive at should look something like this. So now we're integrating, and let's integrate from basically temperature 1 to temperature 2, and again basically from pressure 1 to pressure 2, I believe. Yeah, that basically works. I think it's good to note that pressure 1 and pressure 2 are both saturation vapor pressures as well, so I'll go ahead and even denote them as that. And from here, with this integration, we will then, this will be the final step in this derivation. So let's go ahead and do it, and hopefully I won't make any integration mistakes here. So then that's t to the negative second, and its integral should be something like this. There we are. T, and this should be, you know what, I'm even going to put t out here, 1 over t2 minus 1 over t1 is equal to, we have 1 over our saturation vapor pressure here, so that should be natural log of P2 sat minus natural log of P1 sat. And of course we can go ahead and use our log rules. I'm going to flip the sides of the equation for this as well, as this is how it's generally written in textbooks. Times 1 over T2 minus 1 over T1. And there you have it. You've derived an expression now to relate temperatures, which is something fairly easy to measure, right, to what the saturation vapor pressure of that component will be. And what's really fascinating about this derivation is it comes virtually solely from a theoretical thinking model rather than any actual experimental data or measurements in order to derive this kind of expression here. So there you have it. This is what's generally referred to as the Clausius-Clapeyron expression. So this is, again, Clausius-Clapeyron, and we derived Clapeyron. What's interesting to note about the Clapeyron expression as well, I meant to mention this earlier, but I'll mention it now. You actually have similar expressions for this, for the solid liquid phase equilibriums as well as the solid vapor phase equilibriums. Obviously, change in enthalpy of vaporization will become change in enthalpy of melting or whatever in order, or sublimation as such, in order to derive those expressions. However, all of the other terms would basically remain the same, and you could derive the pressure that would work to have some sort of equilibrium between those phases as well. So I think that's fairly interesting. And yeah, that is all for this video, and kind of wraps up our discussion on thermodynamics. Thank you much for watching.